let's learn how do we measure directions in a crystal lattice. Okay, we do that with the help of a concept known as crystallographic direction indices. Okay, so let me just tell you what is the definition of crystallographic direction indices. Crystallographic direction indices basically are the vector components of the direction resolved along each of the crystallographic axes. Okay, so these are my crystallographic axes and reduced to smallest integer. Okay, just understand what this means. Let's just say that I have a lattice point over here. Okay, this is a cubic cell whose dimensions are unity. Okay, so I'll just write it down for you. This is a cubic cell where A is equal to unity, which is 1. Okay, so there is a lattice point over here. I want to specify the direction of this lattice point with respect to the origin over here. Okay, since I have chosen my crystallographic axis like this, my origin is over here. I can choose my crystallographic axes anywhere, and corresponding to those crystallographic axes I am going to get a different origin. At this particular moment I am assuming this is my origin and I want to specify the direction at which this lattice point is located. So what we are going to do is first find out the vector representation of this direction. Okay, what is this direction? We are looking at this direction. Okay, so how are you going to get the vector representation of this direction? What is the coordinates for this lattice point? You go 1 units in y direction. Okay, this is a cubic cell of dimension 1. So you go 1 units in y direction, then you go 1 unit in x direction and 0 units in z direction. Okay, therefore the coordinates for this guy would be your y is 1, your x is 1 and z is 0. So it's gonna be 1, 1, 0. Okay, your origin is always 0, 0, 0. So the direction for this guy is 1 minus 0, 1 minus 0, 0 minus 0. Right? So if you were to represent it in a vector, it's gonna be 1 minus 0 I plus 1 minus 0 j plus 0 minus 0 k. Okay, where I, j and k are unit vectors along x, y and z. Right? So as per the definition of crystallographic direction indices, these are the vector components of direction resolved along each of the axes and reduced to smallest integer. Okay, so this is my vector, which is basically 1i plus 1j plus 0k. Now these are to be resolved along each of the axes and reduced to smallest integers. Okay, so along x-axis you have 1 units, along y-axis you have 1 units, along z you have 0 units. Okay, so you have resolved this vector which represents this direction along x, y and z axes. You now also have to reduce it to the smallest set of integers. Now 1, 1, 0 is anyways the smallest set of integers. You cannot reduce them further. Therefore, crystallographic direction indices is going to be 1, 1, 0 represented in or written in square brackets for this direction. Okay, just realize your crystallographic direction indices represent a direction, they do not represent a location of a lattice point. Okay, so it only tells at what direction with respect to the origin is a lattice point or a plane present. Okay, so let's suppose you are considering a FCC lattice. Okay, so over here at the center of this face you are going to have a lattice point, right? So what are going to be the coordinates for this lattice point? It is going to be, you go 1/2 along y direction, you go 1/2 units along x direction, and you reach this lattice point, right? So the coordinates for this guy is going to be what? It is going to be x is half, y is half, and z is 0. Okay, now let's find out the crystallographic direction indices for this particular direction, which is this direction. Obviously we know this direction is same as this direction. Okay, so the crystallographic direction indices for this guy should be same as the crystallographic direction indices that we have calculated over here. Okay, so now let's calculate the crystallographic direction indices for the purple colored direction that I have represented over here. Okay, so first what you're going to do, you're going to get a vector representing this direction. Okay, so what is the vector representing this direction? It's gonna be 1/2 minus 0 I plus 1/2 minus 0 j plus 0 minus 0 k, right? So it's gonna be 1/2 minus 0 I plus 1/2 minus 0 j plus 1/2, not 1/2 rather, plus 0 minus 0 k. Okay, so we are left with half I plus half j plus half k. Now this vector is to be resolved along crystallographic axes. So you have half unit along x, half unit along y, and 0 unit along k. Okay, this is 0. 0 minus 0 is 0. Now my definition tells me it is the vector components of direction resolved along the crystallographic axis is reduced to smallest integer. Okay, now half is not an integer, it is a fraction. Okay, and so is this half. So we have to reduce these three set of numbers to smallest integer. So what we are going to do is multiply all of them with 2. Okay, so I'm just going to write in over here, multiplying all of them by 2. Okay, why did we not multiply by 4 or 6? Look, if you are multiplying with 4, what you're going to get is 2. Over here you're going to get a 2. Okay, 4 into half is 2 and 4 into 0 is 0. 2 to 0 is not the smallest set of integers. Okay, your smallest set of integers is going to be 110 when you're going to multiply this with 2. Okay, your smallest integer is 1. Okay, if you have 1 upon x and you have to make it an integer, you're going to multiply it with x, right? And you're going to get the smallest integer, which is 1. So over here, in order to get the smallest integer, which happens to be the numerator 1, we are going to multiply with the denominator 2. Okay, so my crystallographic direction indices for the given direction would be 2 into half 1, 2 into half 1, and 2 into 0 again 0, which is 110. Okay, so just see, we have got the same crystallographic indices as we had got earlier, because both of them are representing the same direction. Okay, this direction is same as this direction, which is same as this direction, right? So any point along this direction, if you are going to calculate the crystallographic direction indices with respect to that point, it's gonna be 110. Okay, Now let's say that I want to find out the indices which represents this direction. Okay, this is just the reverse of what we have already calculated. So let's see what is the crystallographic direction indices for this direction. This is a point at the center of the base having coordinates half half 0, and this is origin which is 0 0 0. Okay, so in order to get the indices, what you're going to do, first you're going to represent in vector form, then you're going to resolve along x, y and z axes, and then you're going to reduce to smallest set of integers by multiplying all the numbers which have been resolved by a common number. Okay, so if you've got, let's say, alpha, beta, gamma, after resolving, then you're going to reduce all of them to smallest set of integers by multiplying each one of them with a number k. Okay, it has to be a single number that you're going to multiply all of them. Okay, so let's do this. First I need to get the vector that represents this direction. What is the vector that represents this direction? It's gonna be 0 minus half I plus 0 minus half j plus 0 minus 0 k. Okay, so I'll just write it down. 0 minus half I plus 0 minus half j plus 0 minus half, not 0 minus half, rather 0 minus 0. Okay, we have a 0, we have a 0, so 0 minus 0 k. This is basically equal to minus half I minus half j plus 0 k. Okay, so your next step is to get this vector resolved along x, y and z, right? So along x you have minus half, along y you have minus half, along z you have 0. Okay, obviously these are not in integral forms. This is not an integer, this is a fraction, right? So you are going to reduce it to smallest integer by multiplying each one of them with 2. Okay, so you have 2 into minus half, 2 into minus half, 2 into 0, which gives you what? It gives you minus 1 minus 1 0. Okay, now minus 1 you represent as 1 bar. Okay, so you have 1 bar 0 as the crystallographic direction indices for this direction. Okay, just realize earlier direction was 1 1 0, or earlier direction indices were 1 1 0, and this is 1 bar 0, which is just the reverse of the direction that we had calculated earlier. Okay, so when you have negative integers, you represent them with a bar. Okay, let's take yet another example. Okay, we now want to find out the indices for this particular direction. Okay, this direction. What is this direction? This direction is over here. You have a point whose coordinates are, along y you go 1, along x you go half, and along z you go 0. Okay, so along x you are going half, along y you are going 1, and along z it is 0. So this is half 1 0, and what is the coordinate for this point? Along x you go 0, along y you go 0, along z you go 1. Okay, so it's going to be 0 0 1, right? So the vector which represents this direction is going to be 0 minus half. Okay, I plus 0 minus 1 j plus 1 minus 0 k. Okay, so this basically gives me minus half I minus 1 j plus 1 k. Okay, so after resolving I am going to be left with minus half, minus 1 and 1. This guy is not an integer. I have to reduce it to a smallest integer, so I am going to multiply it with 2. Okay, just realize, had this been minus 1 by 3, you would have to multiply everyone with 3. Okay, so over here now I am going to multiply everyone with 2, so I am left with 2 into minus half, 2 into minus 1 and 2 into 1, which gives me minus 1, minus 2 and plus 2 as the direction indices for this particular direction. Okay, just realize, had this been minus 1 by 3, minus 1 and 1, then you would have multiplied with 3. Okay, so it would be 3 into 3 into minus 1 by 3, 3 into minus 1 and 3 into 1, and the corresponding indices would be minus 1, minus 3 and 3. Okay, so since we have seen the examples in which the denominator happens to be 2, we have multiplied by 2. Okay, but you have to choose a number which basically reduces it to smallest integer. Okay, so in general, let's just say you have 1 by 2, 1 by 3 and 1. Okay, so obviously these are not indices, these are the resolution along x, y and z. Now if you have to get the indices, you have to reduce them into smallest set of integers. Okay, so now what you're going to do, you're not going to multiply with 2, because if you're going to multiply with 2, you're going to have a 1, but this would become 2 by 3 and this would become 2. This is not an integer, this is still a fractional, so you're going to multiply with 6, right? Once you're going to multiply with 6, you're going to have 3, 2 and 6, and this would be your directional indices along that direction. Okay, so just realize what you have to multiply in order to reduce it to smallest set of integer. Okay, so this happens to be LCM of these two. So what's the final answer for our indices for the direction? The answer would be 1 bar, 2 bar and 2. Okay, we do not have negative numbers in indices, rather what we have is bars. Okay, so the indices which represent the direction, which is this direction, is 1 bar, 2 bar and 2. Okay, so that was about your crystallographic direction indices. Okay, just realize your direction indices are going to change if you are going to change the origin. Okay, we consider some directions to be equivalent. So what are your equivalent directions? Equivalent directions are the directions that can be related by the symmetry operations of your crystal lattice. Okay, so I'm just going to write in over here that directions which are related by the symmetry operations of your lattice are equivalent. Okay, so directions which are related by the symmetry operations of the lattice are said to be equivalent, and we say that they belong to the same family of directions. Okay, we represent a family of directions within angular brackets. Okay, so in a cubic lattice we say that 1 0 0 is a family of equivalent directions, which is your direction 1 0 0, which is your direction 0 1 0, which is your direction 0 0 1, it is your direction 1 bar 0 0, okay, 0 1 bar 0, 0 0 1 bar. Okay, we say that all of these 6 directions, they are equivalent, and we put them in a single family represented by 1 0 0. Okay, in general, if you're talking about a cubic lattice, then your family of directions A, B, C, okay, do not confuse these with lattice parameters. I'm just assuming A, B, C are 3 integers. So your family of direction A, B, C is basically going to be composed of all combinations of A, B, C along with signs. Okay, so it's gonna be A, B, C, A, C, B, okay, B, C, A, B, A, C, all the combinations along with signs. So if you have A, B, C, then A bar B, C would also be equivalent, and so would be A, B bar C. Okay, so if I ask you what are the set of directions that represents the family 1 1 0, what would be your answer? Your answer would be the set of directions that represent family of directions in a cubic lattice would be all the combinations of 1 1 0 along with the signs. Okay, so you are going to have 1 1 0, okay, you are going to have 1 0 1, okay, you are going to have 0 1 1, okay, what else can you have? If you have 1 1 0, then you can have 1 bar 1 0, right? We are talking about all the combinations including the signs, right? So even this is possible. What about 1 1 bar 0? Even this is possible, right? Then if you have 1 0 1, then you can have 1 bar 0 1. You can also have 1 0 1 bar. And if you have 0 1 1, then you can have 0 1 1 bar. You can have 0 1 bar 1. Okay, so how many have you had up until now? It's 3 plus 3 plus 3. You have 9. Okay, if you again look at this, you can even have 1 bar 0. Okay, if you again look at this, you can even have 1 bar 0 1 bar. Okay, and if you again look at this, you can even have 0 1 bar 1 bar. Okay, all these are combinations of 1 1 0 along with the signs, right? So basically this family in cubic lattice is equivalent to 12 directions. Okay, so these 12 directions are said to be equivalent. Okay, they can be transformed into another by means of the symmetry operations of your crystal. Okay, so that was about the family of directions, which are the directions which are equivalent or the directions which are related to the symmetry operations of your crystal. Okay.